Thanks. So we can start with the presentation. Uh, this is about implementation of signal processing algorithms in hardware. It will be mainly focused on some modeling of signal processing algorithms, which helps in optimized implementation of them in the hardware. Before we go, very quick uh, discussion of two properties of DSP or digital signal processing algorithms, which will be quite crucial. Number one, most DSP algorithms are expected to run in real time, so they have to meet speed constraints. Sometimes we kind of misunderstand the meaning of the phrase real time. Real time basically means that the algorithm has to stop, has to process within a certain time frame. That time frame can be anything, but as long as it is guaranteed to finish the processing of certain batch of samples within that time frame, that is called real time. So a real time can come with a guarantee of processing everything within a day also. So that's still real time, as long as all the processing happens within one day. So we have to define the real time with a time constraint within which it finishes the processing. The second property of DSP algorithms is that most of the algorithms are assumed to be non-terminating. So in other words, they get continuous samples and they have to work on them continuously. Simple example of a DSP algorithm, basic FIR filter. So you have two delays, so it gets delayed by 1, then multiplied by B, and then delayed by 2, and then another multiplied by C, and then you add them. This is classic DSP operation or classic linear DSP operation. It's so common that there are hardwares which optimize to implement just this chunk of work, that multiply and add, which is also called multiply and accumulate, or MAC. And the optimized DSP algorithms, DSP architectures try to implement single MAC within one clock cycle. So they're hardware optimized to work on lots of MAC operations. That's one way to represent the DSP algorithm, writing an equation. Another way would be to draw a block diagram. Again, trying to draw the block diagram of the same equation. So comes xn, one delay xn minus 1, another delay, and xn minus 2. And then you multiply each of them, and then you accumulate or add all of them. Mostly, it's better to use generic blocks. For example, you can also use a 3-input adder, but it's better to use like uniform adders, which take 2 inputs and give 1 output. Now, one advantage of this type of block diagram is that it makes it very easy to write down the Z transform of this operation, and vice versa. Given the G transformation, you can easily write down the block diagram, because each delay is basically multiplying with Z to the power minus 1. And of course, once you have the G transformation, you can look at the region of convergence and those kind of things. But the problem is that this is fine for small algorithms where you have got a few number of multiplications and additions, but it's not great for if you have got 100 multiplications or 200 additions, complicated algorithms. Then it's not easy to visualize all those things. And secondly, we just don't want to look at the algorithm in the implementation in a block diagram. We want to do something about that. We want to optimize the implementation of that. That means if possible, we should be trying to borrow from some certain mathematical branch. It happens that we can actually redraw this thing as a network. And in that case, we can reuse or borrow theorems from network analysis and then use here. In terms of redrawing it in terms of like a network, there are two accepted or two common ways of doing that. One is called a signal flow graph. So again, just like any network, it has got nodes and directed edges. In signal flow graph, the nodes represent computations or tasks and some all incoming signals. So each node will take the inputs and sum it, or certain operations like a multiply, something like that. Now, the edges denote linear transformations. They can be either delays or scaling operations like a multiplication. So this one shows the same block diagram in the form of a signal flow graph. Now, again, it's good that it is now transferring the block diagram to a network. We can use network theorems, but it's at a much more granular level. Like it's like each node is just representing additions. It will be better if each node can represent any arbitrary size of operations, and that's what takes us to the next way of representing hardware in like a network. It's called data flow graph. So in data flow graph, the nodes represent computations. It can be in big or small computations, can be a function, subtasks, yeah. And the directed edges represent data path. So a simple directed edge from node A to node B implies that the operation happening in node A has to finish and give the output to node B. So for node B to start working, it needs the output from node A. That is the meaning of the directed edge. And we can also add like the delays can be represented on these directed edges as well. So which means that in a DFG or data flow graph, just the edge itself is describing a precedence constraint, which means that if there is a edge from A to B, as we discussed, operation A has to finish before the operation B can start. Now, okay, this is a simple block diagram again, but this time we have got a block diagram with a feedback. So it's actually an IIR filter. And of course, you can try to see if we can draw the J transform of this operation, because as I was saying, it's easy to write down the G transformation of an operation just by looking at the block diagram. Now, for this, of course, this is G is equal to 1 by 1 minus 8 times J to the power minus 1. And as I was saying, looking at this, you can also find out the regions of convergence quite easily. Now, okay, so that's about the constraint or precedence constraint. The second thing that is important in terms of signal processing algorithm implementation is what is called critical path. Now, critical path in a DFG is basically the longest computation or the longest chain of nodes without any delays. So which means that if there is a chain of nodes in a DFG without any delay, then all the operations in that chain has to happen within one clock cycle, because the last node will require the input from the one before that, which will require the input from one before that. So which implies that all the operation should be finished within one clock cycle. So the clock cycle has to be long enough to accommodate that, which means that if you want to use a faster clock cycle, you can't. So the critical path basically gives the limit of the clock cycle that you can use. So the fastest clock cycle you can use is equal to 1 upon the time taken to process the critical path. For example, in this simple example, the critical path here is the one shown in the red block, consisting of one addition operation and one multiplication operation. So the critical path is TA, or time taken for one addition, and TM, time taken for one multiplication. And the sample period has to be greater than that. Now the sample period also determines the throughput, or the rate of data coming into the DSP architecture and going out from the DSP architecture, which implies that uh, the faster clock we can use, the faster data rate we can accommodate. That's one thing, throughput. There is another figure of merit called latency. Latency is basically how long it takes for the input, or one input, to be processed through the DSP architecture or the algorithm, and the corresponding output to come out. Sometimes latency is an issue. Of course, you can't wait too long, but sometimes latency is not exactly an issue. So latency determines the real-time constraint. So before how long you are expecting the output. Most of the times it's not a huge problem. But again, these are two figures of merit we have to be mindful about. And as we will see very soon, we can actually gain throughput, or we can increase the throughput at the cost of latency. So another simpler example, same a little bit bigger FIR filter. Now you can see that this path in which the input travels to create the delayed versions, it has got lots of delays. So this path is definitely not the critical path. The critical path is the one where this multiplication with the scale A happens, and then followed by 4 additions. Now, if time taken for one addition is 4 nanoseconds and the time taken for one multiplication is 10 nanoseconds, then the critical path here corresponds to 26 nanoseconds. So the fastest clock cycle you can run on this architecture is 1 by 26 nanoseconds. Now, how can we make it any faster? So by definition, if we can make the critical path smaller, then we can run it at a faster clock cycle. And how to make it smaller? If by some way we can actually add delays in the critical path, so that ultimately reduces the size of the critical path. But if we start adding arbitrary delays, that will change the functionality. So a lot of optimization of DSP algorithms is basically about how can we add delays without changing the functionality of the algorithm. So that's what we'll see in the rest of the discussion, like how can we add delay without changing the operation, the function. One method is called pipelining. Yeah, so it's kind of it kind of follows the allegory of water going in a pipe and coming out at the other end. So the longer the pipe you can use, you can take, you can put the water faster. What it basically means is you reduce the critical path, and how do you do that? You add delays, which means that if you can do this thing, if you can add delays without changing functionality, it will of course increase the throughput, but at the cost of longer latency. One easy way of adding delays, and this one applies for feed-forward architectures only. If there are feedback paths, it will not apply. So just two very quick definitions. A cutset in a graph is set of edges such that if these edges are removed from the graph becomes two disjoint parts. It's basically taking a knife and cutting it up. So that's what it basically means. And a feed-forward cut set is a cut set in which when you cut that graph into two parts, each of the edges you cut are flowing in the same direction. Example is this one. So if you cut, a part of this graph, you can see that the edges that a line will cut, they all flow from left to right. So this fits the definition of a feed-forward cut set. And how do you add delays? So we can add delays on a feed-forward cut set of any MAC structure without affecting the functionality. So if we can find a feed forward cut set, we basically add one delay in each of the edges that it has cut. So for example, in this particular case, if you want to have one cut set, let us say the one just after in between the multipliers A and B, then you can add a delay here in the path that in which the path going from multiplier A towards the next addition, and you'll also need to add another delay in the path in which xn becomes xn minus 1. And you can do the same thing and thereby reducing this big long critical path that we discovered previously. So what do you get? You are getting a much smaller critical path, but what do you lose? You are also adding extra delays in the main path of the input. So you are all, if you want to have 4 delays added in the addition path, then you also need to add 4 extra delays in the input path. But yeah, it's as simple as that. So you basically, if you want to add delays, you try to find out a feed forward cut set and try to add a delay in each of the edges. But not all the algorithms are feed forward, because we also have got algorithms with feedback. So in that case, this will not work. We need to find something better or something more holistic. Then that brings us to the set of algorithms called retiming. In pipelining, we saw that we can actually add extra delays. If there are feedback paths, we can't add extra delays. We can redistribute the delays, but we can't add extra ones. Now, yeah. So which means that retiming doesn't exactly affect latency. It can reduce critical path if we know how to distribute the delays in the algorithm or in the implementation. Now the question is if we cannot add extra delays, what do we do? Like, because if there is a big critical path, and where do we exactly get extra delays from? So because we have to have delays in the network to distribute it, right? Without extra delays, how do we distribute the delays? Now, an easy way to fix this is to basically add a bunch of delays at the input and at the output. So, and once those delays are added, then they become a part of the network and then they can be redistributed. So, yeah. So you can actually add as many delays as required at the input, and then followed by that, go for retiming. Some simple heuristic retiming algorithms. One is called node retiming. What it says is that if you, the picture quite nicely describes this. So if you have some delays in the node, in the edge going into the node, if you subtract certain delays from that, then you have to add the same number of delays in each of the paths coming out of the node. So in this particular case, the incoming node had 5 delays and one of the outgoing node had 1 delay, the other one had no delays. If you reduce the 5 delays into 3 delays, you basically have to push 2 delays into each of the outgoing edges. So the 1D becomes 3D, and where there is no delay, it becomes 2D. The other heuristic retiming algorithm is called Cutset retiming. It's very similar to the one we saw for pipelining, but here you can't add extra delays. So what it says is that you find a cut set, find all the edges that it cuts. So if you decide to reduce one delay from all the left going edges, then you can add one delay to all the right going edges and vice versa. So in this small example, the red line shows one cut set, and the black ones, black delays shows the delays before retiming. So in this particular case, all the rightward going edges, one had 2 delays, another one had 1 delay. If you decide to subtract 1 delay from all the right going edges, then the 2D becomes 1D, and the one where there is 1D, it becomes 0. Whereas all the rightward going edges can now get 1 extra delay each of them. So that's nice. But the problem is that what if all the edges going right do not have delay to give up? So if the edge joining C to E, luckily it has 1 delay. If it had no delay, you can't exactly apply retiming to this network. That is one problem. So it takes a lot of serendipity to apply this thing. Secondly, for a small network, it makes sense. You can look at that, you can try to put your mind and try to find it out. If the network, let us say, has got 50 nodes and I don't know, 100 edges, then finding the best path to put the retiming, that's a bit tricky. So that is where we can go for the more formal definition or the more formal retiming rule. So this we have just borrowed from graph theory, and it's quite simple. So basically, you start with a network, and this network is basically your DFG, the data flow graph, and for each node, you assign an arbitrary number. It's up to you. You can assign any number. Once that has been assigned, you can take any edge. So let's say from U to V, there is this edge W. After retiming, so if you change the W to W dash, where W dash is equal to W plus RV minus RU. And remember that these RVs and RUs are those randomly assigned numbers to each of the nodes. So you assign the numbers and you apply this transformation. So every edge or the delay in every edge is changed using this rule. What it says is that if you do this, like assign random numbers or arbitrary numbers and change every delay, change the delay in every edge following this rule, then the functionality of the graph remains the same. That does not change. Now that's all well and good. If you think a little bit, it can actually create, you can't exactly assign arbitrary numbers. You have to be a little bit careful because there is subtraction here. You want to make sure that the resulting number of delays does not become negative. So basically, you want to make sure that the retime delay has to be always greater than or equal to 0. So that kind of gives us a list of inequalities. So now you can't just arbitrarily assign any numbers to the nodes. The numbers you assign to the nodes have to be the solution to this list of inequalities to make sure that in the resulting graph, there is no edge, there should be no edge with negative number of delays. And of course, once you have that, it's just a matter of solving these inequalities. In addition to that, you can add other criteria. So for example, if you know the best speed that you want to achieve, the data speed you want to achieve, then accordingly you can decide what is the longest critical path you can tolerate. And accordingly you can set that also as another criteria and run your solution of the series of inequalities. The good thing is that using this rule, you can actually write an algorithm which will retime any given DFG. And that's kind of what many of the hardware optimization softwares do, starting from your MATLAB DSP implementation software, which converts your MATLAB code to FPGA, or to something more sophisticated like Synopsys, which helps us to design application-specific ICs. Okay, that's kind of end of the talk. So basically, we discussed two things. Number one, that we can represent DSP algorithms like a network, which is called DFG. And once that representation is there, we can borrow different rules. And one of the rules that we can borrow from network theory or graph theory is to retime, which will basically help us to reduce the critical path, and thereby it will also help us to make the speed of the whole process much faster. Thanks. I see that